Antarctica, a place of such profound, crushing hostility that it makes the surface of Mars look almost welcoming. Here, temperatures plunge past 80 degrees Celsius, winds exceed 100 miles per hour, and the sun vanishes for months, plunging everything into a lethal cryogenic darkness. But the greatest challenge isn't the cold. It's the fact that the very ground, miles of ice, is constantly flowing, shifting, and breaking. Any structure built here is guaranteed to be crushed, buried, or dragged out to sea. Yet, humanity demands a permanent presence on this continent for science. This is the story of the Antarctic superstations, the mega structures that are not built to stand still, but to dance with the ice, defying the forces of nature in the coldest, driest, and windiest place on Earth. For decades, the story of Antarctic construction was a cycle of inevitable failure. Early bases established during the International Geophysical Year in the 1950s were built directly on the snow and ice. The assumption was that they would be permanent. This assumption was fatally flawed. In areas of high snowfall like the British Halley Bay, the annual accumulation is measured in meters, not centimeters. Structures built on the surface quickly became buried. As the snow compacted, it turned into solid ice, crushing the buildings from above and the sides. Halley was abandoned after only 10 years when it was buried 14 meters deep. At the South Pole, engineers dug trenches, essentially building underground, but even those tunnels eventually compressed and collapsed. The ice was an antagonist, and the engineers were losing. The solution was radical. If you cannot stop the ice from moving or the snow from accumulating, you must build a station that can escape both. The ultimate answer to the moving ice shelf came from the UK's Halley 6 research station. Located on the Brunt ice shelf, this station sits on a 150-meter-thick slab of ice that flows perpetually toward the Weddell Sea at a rate of up to 400 meters every year. To prevent it from being calved off into the ocean as an iceberg, the entire base was designed to be mobile. Halley 6 is not a single building, but 8 separate modular pods linked by flexible gangways. Each pod rests upon giant, sky-fitted hydraulic legs. The design makes the station look like a cross between a giant space caterpillar and a futuristic train. When a massive crack in the ice shelf, a chasm miles long, threatened the station's location, the mobility system was put to the ultimate test. Teams spent 13 weeks physically lowering each of the 8 modules onto their skis and towing them, one by one, 23 kilometers upstream, to a new, safer position. The sheer scale of moving an 80-ton research base across a constantly shifting landscape is a logistical marvel, demonstrating that on the ice, flexibility and the ability to escape an impending natural disaster is the true definition of structural strength. If Halley 6 is designed to escape the moving shelf, Germany's Neumayer Station 3 is engineered to continuously rise above its fate. This 2,300-ton multi-story base is located on the Ekstrom ice shelf, where the issue is not just movement, but relentless snow accumulation, up to a meter of fresh powder every year. If built on the surface, the station would be buried and crushed within a decade, just like its predecessors. The ingenious solution was to place the entire structure on 16 massive hydraulic columns. These stilts hold the entire platform 6 meters above the snow surface. When the annual snow accumulation starts to threaten the building, a team performs a precise, painstaking annual lifting procedure. Hydraulic jacks raise the entire platform by about 80 to 100 centimeters. Simultaneously, snow groomers work beneath the platform, pushing new powder under the foundation pads of the stilts to elevate the base for the next lift. This continual mechanical climbing allows the station to essentially outrun the snow accumulation, ensuring a projected lifespan of 25 to 30 years without the structure ever being buried. Furthermore, the elevation and the building's aerodynamic hull shape allow the ferocious Antarctic winds to scour the snow under the base, preventing the formation of damaging drifts. While the engineering solutions for the ice and the cold are spectacular, Antarctica hosts a darker, more insidious challenge: the human element. Antarctic research stations are, by their very nature, isolated, confined, and extreme environments, often compared to future bases on the Moon or Mars. For the handful of people who overwinter in complete 24/7 darkness, cut off from the outside world for 9 months, the psychological strain can be immense. This intense isolation combined with rigid hierarchies and a lack of outside legal oversight, has led to a significant and persistent controversy around workplace safety and misconduct. Recent confidential surveys have revealed alarming rates of sexual assault, harassment, and intense interpersonal conflict at multiple bases, including US-run facilities. The sheer difficulty of reporting incidents and the necessity of remaining cooped up with an alleged harasser for months until a rescue flight is possible creates an environment where tensions can escalate to the breaking point. The superstations may be engineering masterpieces against the ice, but they simultaneously struggle to enforce a safe and just social environment, proving that the human mind can sometimes be the most fragile and unpredictable component in the entire megaproject. The Antarctic superstations stand as monumental examples of engineering pushed to the absolute breaking point of human ingenuity. Every material, from the translucent, thermally efficient nano-aerogel panels to the low-temperature steel used in the structures, is a carefully calculated weapon against a hostile environment. They are self-contained ecosystems, melting snow for water using waste heat from generators and minimizing their footprint to adhere to strict environmental protocols. These bases are not merely shelters. They are living laboratories designed to survive and study the forces of a planet in flux. They prove that even in a place where life should be impossible, human vision, backed by relentless mega-engineering, can carve out a permanent, albeit precarious, foothold for discovery.